So in this video, we're in section 1.6, and we want to talk about the general Bayes theorem as well as do one more example of Bayes theorem. So first we start with the law of total probability. So let's start with the partition A1 A2 up to AN of the sample space S. So when we talk about a partition, it really just means you've divided up into a bunch of events. So like this would be your first event. So you have an event here, and you have an event here, an event here, an event here, and so you just divided S up into a bunch of different events. You've just divided it up. Okay. Now let's consider an event B. Okay, so here's my B. And what if we wanted to find the probability of B? And we don't know just that. Well, what you could do is you could figure out, well, what's B intersected with this little piece of A? And what's B intersected with this piece of A? And this piece of A, this piece of A, this piece of A, this piece of A, etc. So how can we find the probability of B? We could find the probability of the intersections of B with each AI, okay, and then add them up. So again, you find the probability of each of these little pieces, which is really B intersected with that A piece that's behind it. So the law of total probability says if A1 through AN is a partition of the sample space, then the probability of an event B is probability of A1 intersect B plus probability of A2 intersect B plus probability of A3 intersect B, etc. Or instead of doing intersections, you can find the probability of A1 intersect B by doing the probability of A1 times the probability of B given A1. You can use those conditional probabilities. Now that sounds really complicated. I would never expect you to use this formula by using the formula. Instead, you'll just keep doing what we've been doing, drawing the tree diagrams, and you can just do it intuitively without actually having to think about the law of total probability. And similarly, we have the general forms of Bayes theorem, which is we can rewrite Bayes theorem where if you have the probability of AI given B, we know this to be the probability of AI intersect B over the probability of B. And to find the probability of B, we had to do all of those intersections added together. Or if you're doing conditional probabilities, you do AI times the probability of B given AI, because that's the same thing as the intersection of AI given B. And the probability of B is you had to add all of those together. So in this next example, we're going to do one, again, but we're going to use the tree diagram. And this does only still have two events, but you could do it with more than two events. You just do the exact same thing that we've been doing. So we have a construction company employs several welders who do thousands of welds every year. From previous records, the company knows that 5% of all welds do not meet the industry standards. So that would be defective. And so they have to go through and inspect every weld. The inspector's performance has also been observed. So sometimes they'll classify something as defective, but it's really not. Or they might not classify as defective, but it really is, etc. And so they know things like any weld that is in fact defective will be correctly classified as defective, CD, by the inspector 96% of the time. Or in other words, they just tell us the probability of it being classified as defective, if it is defective, is 0.96. The rest of the time is classified as being good, CG. Any weld that is good will be incorrectly classified as defective 2% of the time. So we're saying classified as defective, if it's really good, is 0.02. And we want to draw a tree diagram to represent all of our possible outcomes associated with the experiment of selecting a weld and the classification of the weld. So when you draw these trees, sometimes people ask me, how do I know which thing I start with? Like, do I start with the D and G or the CD and CG, etc.? Well, sometimes it doesn't matter, like if you're doing dependent events. But in this case, the natural state of affairs is something's either defective or good, and then it's classified. So it's either defective or good. Okay, and then it's either classified as defective or classified as good. Classified defective, classified good. So let's go back up. What's the probability of it being defective? We didn't write that down yet, but the 5% of all welds are defective. So the probability of defective equals 0.05. So we have 0.05, 0.95. Now we said the probability of it being classified as defective, if it is defective, is 0.96. So that means if it is defective, means go along the defective branch. Classified as defective is 0.96. Now what's this branch? They're always complement. So if this is 0.96, you do 1 minus 0.96 is 0.04. Now, if we know it's good, you start off with it being good, probability of CD, given that it's good. So that means go along the good branch. Now the probability of it being classified defective is 0.02. And again, the two branches will always be complement, so 0.02 plus 0.98 gets us up to our 1. Now you find the probability of the intersection, so probability of D intersect CD is 0.05 times 0.96, which gives me 0.048. And find each one is 0.002, 0.019, and 0.931. Again, these are the probabilities of each intersection. And you find probabilities by multiplying along the branches. And notice what probabilities were on this second set of branches? It was the conditional probabilities. So now, part D2, if a randomly selected weld is classified by an inspector as being good, what is the probability that the weld is defective? So they want to know what's the probability that it's defective if it was classified as good. Well, anytime you want to find a conditional probability, start by writing out the definition or the formula. So conditional probabilities, you do the probability of the intersection divided by the probability of the given part, which is classified as good. Okay. So now we come back up. We need to find D and CG, or D intersect with CG. That would be this one right here. D intersect with CG is 0.002. But this is why we like tree diagrams, because nowhere in the problem did it tell you the probability of it being classified as good. You would have had to think really hard and do a bunch of tricky things to figure this out. But with our tree diagrams, it's easy. You want the probability of it being CG. Come back up here and just select everything that has a CG in it. This one has a CG. This one has a CG. Those are the only things that have CGs. So if you want the probability of the CG, you put in everything that had a CG on it. So the 0.002 and the 0.931. That's our law of total probability there. It says if you want to find the probability of CG, you add up every single intersection that has a CG in it. And so our final answer is 0.00214.